Okay, 3.3. Okay, so at this point, what can we differentiate? Let's see. Okay. So yeah, so I read. I haven't had the chance to reply to all the comments, but I read through all the comments, and one comment that was pretty prevalent was we'd like to ask questions about the homework. So that's what we're doing. That's why it's at this time. Okay. So now let's get to the lecture. So 3.3. What can we differentiate at this point? What can we differentiate at this point? At this point, what can we differentiate? What can we differentiate? We have the power rule, right? For a natural number, the derivative of x to the n is n x to the n minus 1, right? Although we don't have it for, we don't have it for arbitrary real numbers, have we?
We know cosine and sine.
We know cosine and sine, right? We can do a little bit of this, and then we have a bunch of rules, right, that allow us to combine things, right? You can take the derivative of a constant times your function, right? The derivative of a constant times your function. We can differentiate the sum of functions, right? The derivative of constant is going to be constant times the derivative. The derivative of sum is going to be the sum of the derivatives. Yeah, no.
Are you writing these under sine of x?
I'm rating these as a different category.
Okay.
Yeah. So we can differentiate monomials, right? We can differentiate what are called monomials, pieces of polynomials, and we can differentiate sine and cosine. And then these are rules of combination, right? We can multiply monomials by constants. We can add monomials multiplied by constants to each other. We could, add and get polynomials. We can add polynomials to these guys, whatever. We can combine them, and we can combine these things. Okay. So right, we can take what are called linear combinations. Of the above. So, for example, you could have 5x to the 10th, minus 3x to the 9, plus pi cosine x plus sine. Right. You can take these sort of combinations that you get by multiplying guys and multiplying guys by constants and adding them together, and we can differentiate anything like that. Any such combination of the monomials and the basic trig functions. So that's what we can do right now. These things are called linear combinations. These sorts of combinations. So you take guys, you multiply them by numbers, and then you add them together. That's a linear combination of the original things. Okay. What about something like sine x cosine x? If I asked you to take the derivative of that at this point, how would you do it? Isaac?
One's f and one's g, and I would do the derivative of the first multiplied by the second plus the derivative of the second plus the first.
Okay, so Isaac is saying, well, there's a rule for products. Okay, so the answer, using the knowledge that we have at this point, the answer is you wouldn't be able to, suppose you don't have that rule yet. Then how, suppose you don't have that rule, how would you do it? How would you do it? Well, you could do it just directly. You could say, well, I'm going to take the limit of f of x plus h minus f of x over h as h goes to 0. Could take this sort of thing, right? But it would be a pain. You know, maybe at this point you use your your addition formulas, right? And then you start multiplying, and then you maybe work out something. Okay, it would be horrible. Okay, so there's one way. You know, at this point this is the only way we could do it. But fortunately we have something better. Fortunately, there's a rule. There's something called Leibniz's rule. Or it's also called the product rule. And it's just what Isaac was saying, that if you have two functions which are differentiable at some point C, then in fact the product is differentiable at C. And the derivative of the product is going to be the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. Yeah, Isaac.
So this is a notation question.
Okay.
The little symbol that goes like this, that's the integral one, correct?
Yeah.
You don't use that ever for
This?
yes.
Mhm.
Okay, so that's.
I was wondering when that was gonna like show up on the board and we was only been using dy dx, and I was like, oh.
Yeah, we're not going to see it for a while. We're not gonna see it for a while. Right now we're doing what's called differential calculus, and then when we get to that, we'll do integral calculus. Okay, so for example, right, if somebody says what's the derivative of sine x cosine x, you wouldn't have to do this limit process, but you could just use the rule and say, well, this is going to be the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. So you get cosine squared minus sine squared. Or if I asked you to differentiate, say, sine x times sine x, take 1 minute or 30 seconds and write down what you'll get using this rule. Okay, turn to somebody nearby and say the answer is whatever. Okay. What's the answer? Who would like to say? Cindy, how about you? Cosine x sine x plus sine x cosine x, in other words 2 cosine x sine x. Right? the same thing. Right, you take the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy.
But then, how come in the example before that, it's sin x times negative sin?
The derivative of cosine, remember, was negative sign. Yeah. So
So that bottom one is the.
Isaac. No. Okay. Okay. Here's another one. X squared sine x cosine x. Okay. So take 1 minute and see if you can do it.
Does the product rule work if I just break it into 3 pieces?
The product rule works for 2 pieces. Yeah. Okay, turn to somebody nearby and say, here's what I'm doing, even if you haven't completed it.
I know that's not like this. Yeah, so if you're putting x with
Okay, would anybody like to say how they're doing it? Present, how about you?
2x times sin x and then plus x squared times cosine x squared, and the cosine squared x minus
That'll do it, right? So what Grace Ann did was said, well, was to say, let's, the product rule is about, the derivative of a product of two functions. So there's a sort of a choice, how you want to split up this product into 2 factors, right? So what she did is take x squared as your first function and sine x cosine x as your second function. You could have done it some other way. You could have said, I'm going to take this as my first function and this is my second function. That would also go. Or you could have taken this guy as your first function and this guy as your second function. That would also go, right? But the reason for doing this is because we've already calculated the derivative of this thing over here, so why not take advantage of that? So you say, okay, well, right? This is our f and this is our g. So the derivative is going to be the first guy, right? I'm sorry, the derivative of the first guy times the second guy plus the first guy, right, x squared, times the derivative of the second guy. Well, we already worked that out, right? That's cosine squared x minus sine squared x. Okay. Right. If we hadn't worked it out, it still would have been fine. We just would have had to work it out at this point. We would have said, you get the derivative of the first guy times the second plus the first guy times the derivative of the second. Right? Suppose we hadn't worked it out already. Then we would have done this. We would have gotten to this point and said, oh, we need to apply the chain rule again. I mean, the product rule again. Sorry. We need to apply the product rule again. And so we say, okay, this is going to be x squared times, well, now we take the derivative, the first guy, the derivative of the first guy times the second guy plus the first guy's derivative, plus the first guy times the derivative of the second guy. We would have gotten. So we would have, if you have something like this, it's just a matter of applying the product rule iteratively. Like you say, okay, I'm going to take this and this. I'm going to take the derivative of this. I need to apply the product rule to this again. So it's not hard. You just end up doing the product rule over it. Any questions about this sort of thing? So this is the product rule. It's pretty handy. Let me explain why we should believe it. Why we should believe it. Right. Yeah, some people, when they're faced with the derivative of a product, they say, well, shouldn't it just be the product of the derivatives? That'd be great, right? That at least it sounds good, right? The derivative of a product is the product of the derivatives. But that's not what it is. It's the product of one derivative against the other guy's function, and then the function against the other guy's derivative. And so let's see how that happens. How does this happen? How does this happen? So consider this derivative. Okay, let's just look at it. The derivative of a product, well, that's going to be what? What should I better read? The limit of what? Needs to go to 0 of, somebody just tell me, Amani? You want to tell me? No. Kayla? The derivative of this function is going to be the limit of
times g of x plus h minus f of x g of x, all over h.
Yeah. Okay. Let me call these guys C's because I called it C over here. C plus h. F of C g of c. Great. Right. That's the definition of the limit. Okay. We pull a trick. As usual, we pull a trick. Okay, and the trick is this. We throw in a 0. Throw in a 0. Here it is. That underlined term is we've subtracted something and we added that same something back. Why do we do that? Because it will allow us to simplify this expression, and we'll see what happens to it. We'll see that it turns into the one that's what we're looking for. hope nobody minds that we throw in the series. It may seem incomprehensible or sort of like bewildering why we do it, but I hope nobody objects to me doing it. Right? We're allowed to add 0. Right? I'm not the boss. Who is the boss? I'm not sure. Yeah, I should stop thinking about this. Who is the boss? Is mathematics the boss? Okay, I'm going to stop thinking about this. There's no time. Okay. Mathematics is the boss. Mathematics is the boss. Okay. Yeah. Okay. So now look at this thing. What do you see? F of c plus h minus f of c times g of c plus h. Yeah, mathematics is the boss. What I mean to say is that no mathematics professor is cool. Okay. It's the mathematics that is cool. Right. Did I make this up? No. I'm just showing you. Okay. And over here, you see what you get. You get g of c plus h minus g of c. Everything over h. Okay. Right. Okay. So maybe now you're starting to see what happens. Right? It's starting to take form here. What happens to this thing? What happens to this thing here? As h goes to 0, what's this? This is the derivative of f at c. Right? What happens to this thing? G of c plus h as h goes to 0. G of c. Why? Because g is continuous. Right? So as h goes to 0, this thing, you just evaluated g of c. Okay? And then, sorry, this should be a plus. Sorry. And then here, well, this f of c, as h goes to 0, that just stays still, right? What about this thing? G of c plus h minus g of c over h. What does that turn into as h goes to 0? G prime. And you see what happens, right? So we get f prime of c, g of c, plus f of c, g prime of c. So this is how the formula shows up. This is how the formula is derived. Okay. So last bit in this section. So at this point we can now do products of everything that we had before, right? You could have a polynomial multiplied by something, that thing, and multiply that by some polynomial. Whatever, you can take whatever combinations, we can do all these sorts of combinations at this point. Okay? It'll be a pain, but you can do it. So there's one last skill in this section, which is derivatives of quotients. Okay, so if you have a function divided by another function, and you want to take the derivative, of that. Okay, so you have f and g differentiable at c, and g of c is not 0. Then this thing is called the quotient rule. Quotient rule. what do you get, those of you who've had calculus before? Jennifer?
G f prime, or G times f prime, let's see, minus f of c times g prime of c divided by g of c squared.
Mhm. Okay. So this is formula. I'm not going to prove this one. The proof of this is a little bit, it's not that much harder than this, but it's a little bit harder, and we're not going to do it. But we're just going to use it. So, for example, right, if I ask you the derivative of the tangent, well, that's the derivative of sine over cosine. And so you say, well, okay, I'm going to get the bottom times the derivative of the top minus the top times the derivative of the bottom, everything over the bottom squared. Right. Bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. Right? And so you see that you get cosine squared plus sine squared on the top, which is 1 over cosine squared. So that's secant, so-called secant squared. That's 1 over, you get 1 over cosine squared, also called secant squared. Just for practice, let me put up one. This is not, it's just remembering what the formula is. So take 1 minute and just differentiate this thing. Okay, turn to somebody nearby and say what you got. Or say what you're doing if you haven't finished. Okay, so what do you get? Would somebody like to say how to do it? Noora, I'm gonna pick on you. You looked up.
No, I was confused because I didn't know if you were supposed to break up x minus x like f and g, but I found that this f.
Yes, this is one function. This is the numerator function. This is the denominator function.
Would it be x minus times cosine 1 of 1 times
So how do you differentiate this guy? Use the product rule. So you say the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. So use the product rule.
cosine over
Don't forget minus,
oh,
right? The bottom times the derivative of the top minus the top times times the derivative of the bottom guy. Well, what's the derivative?
1 plus cosine.
Mhm. This thing times 1 plus cosine all over,
X plus sin x squared.
yes. Great. Okay. So bottom times the derivative of the top, which we get by using the product rule, minus the top times the derivative of the bottom over the bottom square. So pretty straightforward. Yeah, Isaac.
Can you simplify it by breaking it down?
Yeah, probably.